Let's Boltzmann Q&A. Today's question comes out of the lecture. I was asked what is the meaning of the moments. So before we come to the meaning of the moments, of course, we have to start saying what moments actually are. And moments are integral properties of a distribution, which we have here as f in a variable xi in this case, and they are integrated over kernel phi, and this gives us the moment m phi. So this is in general the definition of the moments. A somewhat more useful way to see moments is through the moment generating function, which also kind of explains where we are going to. So the moment generating function is the Laplace transform of the moment of the distribution function, where unfortunately, due to the way it was defined, we have to take the Laplace transform of the distribution function according to the negative sign of the variable that we are integrating over. And then we take derivatives of this Laplace transformed distribution function in the Laplace transform of the independent variable xi. So capital Xi is the Laplace transform of the small xi. So, and this gives us, of course, so this is the definition of the Laplace transform, of course. So this gives us the coefficients of a series expansion of the Laplace transform of the distribution, right? So this is the same thing that you would do if you take a Taylor series expansion. You would take the derivatives, and there would be an additional factor in front of it by 1 over the order A factorial. Yeah, so this is left out here in this case. But we get these moments, a hierarchy of moments, as the series expansion of the Laplace transform of a distribution function. So this seems to be a little bit involved, but in particular in the case of distribution functions in kinetic theory, this kind of makes sense. So why do we look at the Laplace transform of the distribution function and not of the distribution function itself? Well, the distribution function, in particular if we talk about a particle distribution function, may not be a continuous function of which you could take a series expansion. Yeah. So in general, this distribution function can be made up of discrete particles, for example. Yeah, and they would be represented as Dirac delta distributions in F. So fortunately, if you think about the Fourier transform or the Laplace transform, both behave here in the same way. The Fourier transform or the Laplace transform, so the Laplace transform here is written as the capital F, where the original distribution is the small f. The Laplace transform of a discrete distribution is a continuous distribution. So starting off with this discrete distribution of particles in velocity space, we come to a continuous distribution in the Laplace transformed velocity space. And because this is a continuous function, it now can be expanded in terms of a series expansion. So this is what the moments actually are. And now because now we have this series expansion, we actually have a hierarchy of moments, which in the case of the kinetic gas theory would be the moments in terms of in velocity space. So they would be the mass, the momentum, and going on to the energy. So, and these are the lowest order moments. And why we are interested into the lowest order moments is precisely because the lowest order moments are the hydrodynamic moments. So the hydrodynamic moments are the ones on which the Navier-Stokes equation that are required for the Navier-Stokes equation. So there are actually 10 moments that are called the hydrodynamic moments, and these have to be known in order to solve the Navier-Stokes equation, and they are related to the mass, to the velocity, and also to the energy and the shear rate moments. So these are the leading order terms in the series expansion of this distribution function, of this Laplace transform distribution functions. And there are, of course, infinitely many other moments, but they do not appear in the Navier-Stokes equation. So for solving the Navier-Stokes equation, we don't need to know them. And now some people then say, so because they do not appear in the Navier-Stokes equation, they don't have any physical meaning, which of course is not correct. And the only thing that is correct is that we don't need to know them in order to solve the Navier-Stokes equation. To understand why these things still have a meaning, even though the meaning may not be in a certain limit or in the limit of the Navier-Stokes equation, so we don't need to know them for solving the Navier-Stokes equation. We look at another kind of moments that may be more familiar to you. And these are the moments, the mass moments in space. So suppose you have a body in space, and the body is a distribution of the mass, which we call here rho, in space. So the zero order moment of the mass here of the mass distribution would give you, of course, the mass, which you have to know for describing it. And the first moment, which we normalize here by dividing by the mass, so we have to know the mass, the first moment would be the center of mass. So with the mass and the center of mass, you could describe this thing here already in a kind of a particle. And if you have, in addition to the first moment, also the second moment, so with respect to the center of mass, so we have to integrate here over the location x centered in the center of mass twice, and integrate, and then we get the moment of inertia. And if we know the mass, the center of mass, and the moment of inertia, we know everything that we need to know to describe this as a solid body motion. Yeah? So we need only a finite number of moments to describe the motion of a body as a solid motion. And then the question is, what is about the other moments, the higher moments of the system? Do they add anything to this knowledge? And in a sense they do, and in a sense they don't. The meaning of these moments can be understood like this. So if you have only the first moment, you can describe a body as a particle, So no internal decrease of freedom, it cannot rotate or something, but you can already describe its movement. If you have the second moment, so the moment of inertia, you can describe its movement and its rotation. And this is usually enough to describe a solid body dynamics. But you don't know anything about the form of this particle other than its moment in inertia, and by this, the behavior, it would rotate in space. So if you go on and take infinitely many moments, then you could actually get the entire description of the body. So the entire description of the body is not important as far as solid body rotation goes. So in that sense, the shape of the body does not matter, but this doesn't mean that the shape of the body has no physical meaning. If you want to have a more accurate understanding of how the body behaves, you actually need its entire shape. And the same thing goes for fluid dynamics. Yeah. So for describing the Navier-Stokes equation, we only need a certain number of moments of the velocity moments. Only a certain number of them appear in the Navier-Stokes equation. And this is why they are assumed to be sufficient for describing fluid dynamics. And these are, of course, the low order parts of the expansion of the series expansion of this distribution function. So this leaves us with this description of what moments are good for. Thank you for listening.